Hello, how are y'all doing today? Or how are any of you doing today? Okay, that's a win. I semi heard you. Okay, are you all able to hear me okay? Like a thumbs up.
Yep, we can hear you.
Yay. Okay, so good call. I am happy to announce that everything's good. So I'm gonna just go ahead and start sharing, like just what I normally frickin' do. And we'll see where we get to today. In terms of administrative things, there's nothing really that I think is key other than, geez, it's Thursday. And a week from today, at this point in time, you're probably going to be sitting in a final exam. So maybe prep for that. Second thing I want to mention is for the final exam, maybe I should go to the first page, the home page for the class, if you will. That unlike where you guys have been using this probability distribution calculator, yeah, uh, we're not going to have you do that during the course of the exam. And so things like the t-table, you might want to bring one, okay? And so I'll probably bring you a test, which if you have just the t-table, uh, you should be fine. Okay. Other things that might correspond to like a chi-square table, like we'll talk about today, or the normal table, which you probably have memorized by now. Uh, yeah. So if you bring a t-table, that should be sufficient to tackle any questions relating to a table lookup. And I know that if you can use a t-table, you can use chi-square, you can use the normal. And so if it's really important to me, did I test you on table lookups? Yeah, it'll be in the context of a t-table. But yeah, no, you will not have access to the JMP probability distribution calculator. It'll be like on paper. And every analysis that I'll want you to look at would be right there on paper in front of you. So I want to mention that. Second is it seems as though we're talking about this set of things called basic hypothesis testing. In chapter 8, we sort of focus on the logic of hypothesis testing. And then we talked yesterday about comparing means. Okay. And we're going to sort of pick up today with testing in the context of paired data. And then we're going to move on to talking about if your data naturally would be in percentages as opposed to quantitative data where typically we care about the means. So any questions about my set of administrative announcement-y things?
To confirm, do
Yeah.
we need to bring in our own normal table for any sort of questions, or will it be provided?
Um, I said bring a tea table, and
Okay.
any tea table you want to bring is fine. The normal table, I guess I just decided on the fly that if there was something that mattered to me with the normal distribution, I would show you a part of the normal table, or maybe I would just automate it for you. I mean, it's not like I can't just say, suppose your p-value was 0.03. What would your conclusion be? The automation of the test statistic to p-value, the software just sort of does that for us. But if I have you do a hand calculation, the way I'm likely going to avoid you guys using a table to look up the answers is to simply say something like, okay, what if your p-value were the following? Then what would you do? Okay, so or what if you wanted 95% confidence and you know the normal table it's going to be plus or minus 1.96, but y'all remember plus or minus two, and that's going to be close enough. So I think, John, I answered your question approximately. You want to follow up?
Yep, you're good.
Okay, cool. Anyone else on anything related to administrative issues? Okay, so what I'd love to do is to switch gears a little bit and sort of dive in on our example from last time with our sunscreen and talk about, well, suppose maybe what I should do just have a blank background first, and then talk about the sunscreen. And I'll maybe move these guys off to the side because they're not until later. If we've got data on sunscreen and how long you could be in the sun until noticeable sun damage occurs, we talked last time at the very beginning of class about a confidence interval for mu d. Okay, so last time confidence interval for the unknown mu sub d, the mean of the differences, like literally the average amount of extra time that you could be in the sun until sun damage occurs. That's really what mu d is. So last time, yeah, so that's d bar plus or minus t times s d over the root of n. Okay. What about a test for mu d? And again, typically you might care about something like the following. The null hypothesis could be that mu d is a specified value delta naught. Your alternative might be that mu d is less than delta naught. Maybe mu d is greater than delta naught. Maybe just that mu d is not delta naught. Okay, so there's three possible alternatives. The first one corresponds to, the first group has a lower mean than the second group, if you will. If you're subtracting, okay, control from sunscreen, the group control minus the sunscreen group. If the sunscreen group is able to be in the sun longer, that would be your natural alternative hypothesis. Does sunscreen increase the amount of time? Okay. If it's mu control, I guess control, if your differences, if the D's are literally Y for the control minus Y for the sunscreen, okay, those differences would tend to be negative if your value for Y, S, it tends to be larger than YC. So the natural alternative might be that there is a negative difference. Or perhaps let's go with the alternative that mu D is not zero. Yeah, mu d is not zero. That's a way of saying that there is some effect of sunscreen on your amount of time that you could be in the sun. Okay, I'm not saying whether positive or negative, just that there is some impact. So let's talk about how to pull that guy off. Like we did last time, analyze, well, that sort of specialized match pairs. Yes. And to be honest, specialized match pairs, whatever. Let's just list our two different groups right there, control and sunscreen. You could put them in the other order if you prefer the other ordering for your differences. But we have here sunscreen, I'm sorry, sunscreen minus control. Okay, so it's the second one minus the first one here, the sunscreen mean minus the control mean, if you will, or the mean of the sunscreen value minus the control value. My alternative hypotheses are that mu d is non-zero. That is our p-value for that there is an impact. And our answer would be, because p-value is small, yes, there is an effect of sunscreen. Sunscreen results in a different average amount of time in the sun. If we have the alternative hypothesis that mu d is less than zero, that's going to be the probability in this case greater than t, because instead of control minus sunscreen, we've got sunscreen minus control in the output. Again, you could change that ordering if you wanted to. But I'd say the chance that we are having a t value that's larger than we did observe is tiny. So the question occurs to me, hey, what is that t value? We claim that we know from a p value what our conclusion is. We've got the null and the alternative hypotheses. What is the test statistic? Our test statistic is t. Literally, it's the average of the differences, d bar, minus, well, delta naught, the hypothetical difference, over S sub d over the root of n, the number of nd, the number of differences. So it's a test statistic if I give you things like the average of the differences, the standard deviation of the differences, the sample size of the differences. The calculations are really quick, but the software will just give you all of the same answers. If you got the data in raw form, the software is a great approach. Okay. Any questions about the hypothesis test in the paired data context?
Sorry, could you like repeat how you would interpret it in English one more time?
Interpret what in English? Haha.
Um, like the results, like would you say it's like there's an average difference
Sure.
between?
So I would, if I was focusing on the alternative hypothesis that there is a difference, okay, that would give me a p-value right there, less than 0001. The definition of the p-value says if in fact mu d is exactly zero, if delta naught was zero, if there is no difference at all between the sunscreen and the control at all, then in less than 1 out of 10,000 samples would I see a difference as extreme as this one is. Our mean difference was like 250 minutes. That would just not occur by luck alone. We're saying the chance of that occurring is tiny. Okay. So I would instead believe the alternative. Literally, I'm going to say, yeah, there is an impact or an effect of sunscreen on the amount of time that you are able to be in the sun. If, on the other hand, you wanted to use the first, okay, of the 1, 2, 3 alternative hypotheses, it's a way of saying mu d less than zero, with that definition of the differences. It's saying that on average, the sunscreen value is larger than the control value. And our one-sided, our directional hypothesis test p-value is less than, again, that 0001. I would say I would reject the null hypothesis that there is no impact of sunscreen and conclude that sunscreen allows me to remain in the sun for longer without noticeable sun damage. So Meg or Magnet, is that good?
Yeah, I think I understand now. Thank you.
Do any of you want to follow up on that? Because I think the question's a really good one. Okay. So then moving forward a little bit, then we deal with a different sort of a problem entirely. What if your variable that you want to test a hypothesis about is categorical and would naturally be summarized with something like a percentage? I'm thinking something like this. If I'm going to flip a coin 100 times and I got my Greek euro again, my null hypothesis might very well be that the rate of getting heads with this coin is a specified rate, and I'm going to call that pi zero. In this case, coin is fair, 1/2. On the other hand, I'm claiming that the Greek euro has a rate of coming up heads that's less than pi zero. Again, 1/2. I'd say the rate of a Greek euro coming up heads is less than half. That's my alternative. I'm going to stick with the null. It's like any other coin. It comes up heads half the time, tails half the time. And I'm willing to believe that the rate of heads is lower as long as I have evidence to convince me of that. So in n equals 100 trials, if I get x equals 34 heads, okay, 34 heads, I guess my rate of heads, p hat, is 34 of 100 or 0.34. What should I do with that 0.34? Well, the natural thing to do is to compare the 34% to the hypothetical 1/2 that I would expect to see if really the coin were fair. And I'm going to say my test statistic here is always a comparison of what you do see and what you expected to see if the null hypothesis were true. I'm going to say we did see a certain rate. We're going to compare that to a target level, 0.5, if you will. And we're going to divide that through by the standard deviation of the distribution of the possible p hats, which we know from the normal approximation to the binomial, and then divide through by n. That's going to be pi naught times 1 minus pi naught all over n. So in our case, I get 34% heads in my sample. I expected 50% heads in my sample overall, and we're going to divide that through by 0.5, again, controlled by the null hypothesis. Notice that in the denominator here, we're assuming that pi is pi naught and known to be 0.5. 0.5 times 1 minus 0.5 all over 100. In our case here, we get negative 0.16 over 0.05, and that's negative 3.20. So yay, I got a z-value of 3.20. So it's a calculation, and again, it's a way of comparing what you did get to what you should have been getting if the null hypothesis were true, relative to the amount of spread in the sample proportion around the truth if the truth were 0.5. Okay, so I see a z-value of negative 3.2. P-value is like, how likely am I to see a negative 3.2 or even lower? Negative 3.2 and down. And that chance, is going to be relatively small. So I want to use the z-table to look that up. And so I'm going to remember the z-value is negative 3.2. And let's open up that z-table. Again, I could use the GMP probability distribution calculator, but you shouldn't always rely on the calculator. My standard normal table. I'm going to look up a z of negative 3.2. Negative 3.2 has an area of 0007. My p-value is 0.0007 with 34 heads and 100 flips. I have to believe either the coin is fair and we were just 7 out of 10,000 level unlucky, or believe that the coin is biased and really it's less than half the time coming up heads. And I would conclude the alternative. Now you wonder about that, the Greek euro, am I lying to you? It's actually true of the Belgian euro as well. For whatever reason, those two coins, once statisticians found out that indeed you spin the coin on its edge, it comes up heads less than half. We love to use it for class purposes because everyone assumes coins are fair, and they typically are, but here, no. Okay, so I'd love to tackle questions about that z-test for a population proportion, if you have any. Okay, so I want to now leverage something that JMP does for me. JMP will automatically, in many contexts, come up with a test statistic and a p-value if I just say, hey, please do the thing. I want to show you that that JMP will do the thing for you. And then we're, in this case, going to double back and talk about the actual calculation by hand if you needed to do a hand calculation. So I'll tell you a story first. 2001, the Super Bowl, I believe, was one of my favorite Super Bowls, not because St. Louis beat Tennessee. I don't frankly care who would win, St. Louis or Tennessee, whatever. It just really didn't matter to me. But what I noticed that was super interesting for me is a commercial that showed a happy fat person dancing on the beach, and the voiceover said, if you've been unable to lose weight via diet and exercise, ask your doctor about Xenical. So I'm saying Xenical probably is one of those weight loss medications. And the voiceover then at the very end of the ad said, warning, may cause an inability to control one's bowel movements. And I thought, oh, this is just too good to ignore for class purposes. I'm going to look these data up. And here are the data presented in what's sometimes called awkward form. Let me show you how you might very well present it in a more traditional fashion. Usually on the rows, you have information about your explanatory variable. So are you taking Xenical? Okay. Or are you taking the placebo? It's one or the other. and you either experience, well, Xenical causes an inability to control one's bowel movements. That sounds like the sort of, I guess, the thing that we've got going around the US now. Fecal urgency, FU, is for fecal urgency, or there's FU prime. It's not fecal urgency. It's one or the other that a person experiences. Okay. If you take the medication, either you experience the side effect of explosive diarrhea or you don't. Okay. And there was a collection of people who did take Xenical and experienced fecal urgency, 356 of them. Literally, it's over here in my table, which is off the, there we go. It's in my table there. Hold on. Okay, so I'm going to sort of circle it there. And there were in the Xenical, not Xenical, but yes, did experience fecal urgency. There's 98 of those folks. Okay. Then we've got 1368 in the no category. 1368. Oh, I'm sorry, 1368 and 1557. If you were to add these up, that's 1913 individuals taking Xenical. And darn it, I think I have an error in my data. Okay, yeah, that one's correct, but okay, so 6 and she's 7, 23. Am I wrong on that, or am I right on that one? Yeah, 2476. Okay, so yeah, that's about. Now, sorry, subtracting in my head in front of other people always been an issue. Adding in my head is even problematic. So 1466. There we go, of the 3379 individuals in total. So this is sometimes what's called a contingency table. We're listing off all of the possibilities or contingencies that could possibly occur. Yeah, so you're taking either Xenical or you're not. Okay. You experience the side effect or you don't. Okay. And across the 2 treatment levels, Xenical and placebo, and then 2 outcomes, there's 4 contingencies. And in a contingency table, we have all the information you really need to tackle any of the analyses one would do with the data. The way GMP lays it out is a little bit different. If you have data that's summarized in a table, you're going to list off, well, there's 4 contingencies. There have to be 4 separate rows, one for each of the possibilities. Xenical taking, yeah, you experience fecal urgency, and that's just the count. I labeled it count, but it could be something else like frequency. Took Xenical, didn't have fecal urgency, So there's a lot of ways of describing this, but let's just say the data are sort of summarized in tabular form here. So with this contingency table, this is the way you traditionally present it to a human. Here's how you have to list it off if you're trying to set it up for a proper statistical analysis. Let's talk about actually getting it done. Okay, so under analyze, I'm going to go with fit y by x because that's about what we do these days. And so I have to sort of tell you, what is the response? Well, experiencing the side effect or not may depend on whether you're taking the medication or not. So Xenical or not is your explanatory variable. The response is, do you experience the side effect? It's almost like we were creating a graph, like a scatter plot. You have the response and then the factor that may explain the response. Your results are, sorry, I screwed that up. I need to do that again. I forgot one key thing. I'm going to sort of hit recall. Notice that I had the count and I did not include information about the count. Yeah, the count literally belongs here where it says frequency. How often did each of these 1, 2, 3, 4 contingencies occur? If you don't have a count, it's going to show you exactly what I showed you. So here we have what is sometimes called a mosaic graph or a mosaic plot. And what I see with this is, okay, so I am taking Xenical in the right. I'm not on the left. The rate of fecal urgency in blue. It seems as though the rate of blue is sort of different between the two situations. One might even say it's a little bit higher on the right than on the left. Yay. This contingency table, the way we sort of presented it, it might be a little bit backwards. It's got Xenical no, which we had in the second row, and Xenical yes in the first row. And it also swapped the ordering of no and yes. So that's because it's alphabetical. If we wanted to adjust the presentation and the output, we could, but this essentially tells us in the first number in each of these four cells, the actual count. I usually ignore the total percent. We can even just turn that off. We don't care about the total percent. And you don't even care about the percent in the column of each of the two cases. Okay, let's get rid of that. But this is in this row, the not taking Xenical, there's a rate of fecal urgency of like 6.68%. In the yes, I am taking Xenical, that's 18.6%. Those numbers seem a bit different from each other. Are they statistically significantly different? Is the question. Okay. So how would I say, actually, let's just jump right down to, it seems as though there's multiple p-values, but I'm going to say the one to use according to our textbook is this Pearson. Literally likelihood ratio is not bad either, but it's not covered in our book. So I'm going to say use the Pearson chi-square. And that is a small value, less than 0.0001. I would say I conclude that there is a bit of a difference. Not a bit. There is a difference between the two individual rates. So let's talk about the actual hypothesis test. Let's get into the nitty gritty. We need a null hypothesis. And here's how I'm going to phrase it. The rate of fecal urgency, so the rate of fecal urgency, given that you're taking Xenical, equals the rate of fecal urgency given you're taking the placebo. Okay, so the chance, pi, of fecal urgency, the side effect you don't want to have if you're taking the medicine, is the same as if you're taking the placebo. The rate is the same in the two different groups. On the other hand, I'm going to go with the rate of fecal urgency given Xenical is not equal to the rate of fecal urgency given you're taking the placebo. Some of you might naturally want to say, well, don't you really want to see if Xenical is increasing the rate of fecal urgency? We could go with the alternative hypothesis that's directional, like you're suggesting you might want to see. But GMP does for chi-square, a non-directional alternative. Okay. So our p-value, less than 0.001. What conclusion would you reach? I reject the null. I believe the alternative. I'd say that the rate is different in our two groups. So if you're using JMP to do the work for you, yeah, you would conclude that there is a relationship. Any questions about using JMP for that purpose? Okay, so I want to say I could do the same exact thing with a z-test. And the z-test is literally the basis of that thing we just did called a chi-square analysis. My null hypothesis is that the rate of fecal urgency given you're taking the medicine is the same as the rate of fecal urgency given you're taking the placebo. Our alternative hypothesis is that the rate of fecal urgency given you're taking Xenical is not equal to the rate of fecal urgency given that you're taking the placebo. Those are the two hypotheses. And if the null hypothesis is correct, if the null hypothesis is in fact correct, there is a common rate of fecal urgency between the two groups. How would I estimate that rate? That rate P is equal to the number of fecal urgency cases in the Xenical group plus then the number of fecal urgency cases in the placebo group over the number of individuals in total. So that's N of Xenical plus N for the placebo. That's going to be just indeed our 356 plus 98 over the total, which is 3379. Could I find that average rate? Yes, I can. I can estimate that one common rate, okay, between the two groups. And if one of you is able to calculate that for me, I would really appreciate it. Because our test statistic Z, okay, is literally a measure of difference of our two sample rates. And I'm going to say P, the rate in the Xenical, I'm sorry, the rate of fecal urgency. If one of you does get that number over here on the right, please just shout it out.
I got 0.134.
I love it. It's almost, yeah, I do remember this example. Yeah, that is right. So I'm going to sort of compare the rate in the Xenical group to the rate in the placebo group. So fecal urgency given placebo. And we're going to divide that through. I mean, shoot, the difference should be 0. Okay. We could just take a difference of the two sample rates, and that should be 0 if the null hypothesis is true. The fecal urgency rate in the two separate groups should be about the darn same. If the null is true, it says the population rates are the same. The sample rate should be the same as well. And we're going to divide through by our standard deviation of the distribution of the possible differences of sample means. And that is literally our P hat here, the common rate, times 1 minus P hat, times 1 over N for the Xenical group, plus 1 over N for the placebo group. Yay. And so that is a number. I could find that by hand, but I'm just going to note as a fact, this is Z value. If we square it, we're going to call it chi-square, which is the same thing as the Pearson chi-square that we had just done inside of JMP. So let's go ahead and do the Pearson chi-square again, and this is this data set. And again, if you were to use fit y by x, okay, we would say, recall that, and how does the fecal urgency depend on whether you take Xenical or not? Sorry about that. Fecal urgency depends on Xenical or not. And then the count is your count of occurrence. Your chi-square, your Pearson chi-square value is 101.42. We're home free. We got that 101.42 chi-square value. The square root of that is about 10. My Z value here is about 10. My claim is if we do the calculations, we would get a number almost exactly 10. I tend to rely on chi-square for this, but if you want to follow the book's approach, go ahead and use the Z-test. Works the same. Now, let's talk about how that would come up on a final exam. I could possibly say use a chi-square procedure to compare the rates of success in these two groups. I could say use a Z-test to compare the rates of success in these two groups. If I don't specify, use either approach that you want. You could use the Z thing, you could use the chi-square thing, I don't care. They will give you the same result. Okay. That is if you have two separate levels, sort of Xenical or not, two different options, and fecal urgency or not, again, two separate options. If your response variable isn't necessarily two options, okay, in this case, my example will be with two options, and your explanatory variable isn't with two options, you might still want to tackle the question, is there a relationship between the explanatory and the response variable? The example I want to use is where we had talked about earlier, the Ninana ice flow. And rather than using the scatter plot, where maybe plotting the breakup date since 1900, maybe let's just go ahead and do that graph right now. Rather than using regression to tackle it, breakup date on the y-axis, years since 1900 is along the x-axis. I'm going to ignore the data here, remove the line. I shouldn't say ignore the data. I'm going to say we sort of care about two things. One is whether it's later in the data set or not. It's more recent. Or it's not recent. Okay. And then I clumped the data into three categories vertically, if you will. 120 or less, I call that low. 120 to 128, I'm going to call that medium. Or more than 128, I'm going to call that high. And a natural question might be a natural question that would assess a possible trend, the trend being downwards, is not expressed in terms of a slope, but is the rate of high versus medium versus low different recently than it was before 1980? Are the rates the same? So let's talk about how you could write that out. Okay. So there's recent or not. So the chance of the result being a high number of days since January 1st before ice break occurs, given that's recent, would be equal to the chance that it's a high number of days before the ice breakup occurs, given that it's not recent. Okay, recent or not. So my null hypothesis is that those are the same, and also the rate of it being a medium number of days, given that it's recent, would be equal to the chance that it's a medium number of days, given that it's not recent, and the chance that it's a low number of days, given that it's recent since 1980 in the data set, is equal to the chance that it's a low number of days, given that it is before 1980. So this is what we'll sometimes term a composite null hypothesis. Composite because there's more than one equality. And the logical opposite of all three of these being equal is the alternative, and that's simply not the above. So yeah, literally, if any of those three is incorrect, okay, then I'd say the ice flow breakup depends on whether it's recent or not. Because if this first one is a not equal to, okay, then that says the chance that we wait a long time before the ice breaks up in Nana, that's not the same as before 1980. If since 1980 and before 1980 are less likely to be a large number of days, a cold winter, if you will, then I'd say the ice flow breakup sort of depends on whether it's recent or not. Or if any of these were frankly not equal to, other than the three equalities, if any of those are not equal to, then I guess at least two of them are, and we would believe the alternative hypothesis. How would I tackle that question? Okay. I'm going to tackle it with the chi-square method. And maybe what I should do is to sort of generate the chi-square contingency table using a GMP. We've got the data. Let's generate it. Then I'll sort of work through the equation by hand. And then we'll verify that the answer we get is about the same as if we were using the data. So I categorized the breakup date as is the breakup 1, 2, or 3. Below 120, between 120 and 128, that's group 2, or more than 128, that's group 3. So I've got 1, 2, or 3 for low, medium, and high. And is it before 1980? Okay, if it is, it's not recent. And if it's since 1980, like 2005, yes, it is recent. Okay. So my categorical version of these two quantitative variables are in these last two columns. How would you pull the analysis off? Well, let's just go with the fit y by x again. And I'm going to say where the ice break, low, medium, or high, EMA, early, medium, and late, depends on whether it's recent or not. I click OK. Again, we get this graph, and it seems as though my category 3, which is recent, it's less likely if category 3 means the ice breakup was late in the season, more than 128 days into the new year. That's less likely more recently than it was initially. The first 80 years versus the last 40 years or so The rate of blue goes down. The rate of red seems to be going up. I'm thinking maybe there is a relationship. Again, let's focus on the contingency table. We're shown the contingency table. Let's look at the counts. I don't really care about the total percents, and we usually don't care about the column presents the way I present it. If explanatory is along the row, maybe the percents here, like the percent of early, goes from 20% to 50%, and then sort of a medium goes from 50% down to 37%. And ice breakup being late in the season goes from like 32% down to 13%. It does seem as though there is a trend here. So here's the contingency table, and I want to write down just the counts. Again, the contingency table information is complete with just those counts in our 2 rows, 3 column table. This is a 2x3 table. Here's what we have. Okay, so it's recent or it's not. Okay, and I'm going to sort of reverse the rows. Recent is I guess the early, the medium, and the late. So E, early, medium, and late. Let's put those counts in here. Early on, we had a 15, I guess not early on. Recently, it's been 15, okay, 11, and 4. Okay. And then secondarily, early on, not recently, it's been 13, 30, and then 20. Okay. And so I guess what I could do is just, hey, they're giving me a total. I'm going to copy that down for my own convenience. It's not part of the dimension of the table, but it says 63. No, sorry, got that one wrong. 63 of the data points were indeed way back when, not recent, and 30 of them are recent since, again, 1980. And then early, there's a total of 28. And then we've got 41 and then 24. And the total here is 93 years worth of data. So in the table itself, the 2 rows and 3 columns, that is the dimension here. 2 rows, 3 columns. That is our data. So let's move this over here. So I guess anytime we have a hypothesis test, we have to sort of come up with a way of measuring how closely the data match up to the null hypothesis. And in our case, the null hypothesis says how often you see the high waiting time until ice breakup, a lot of days, it's the same early as late. Okay. The rate of being in this last column is the same, whether you're in the first row or the second row. Similarly, the rate of being in the second column is the same, whether you're in the first row or second row, or even in this first column, the early, it is E for early. There we go. Fix that. Makes me happy. Early is not dependent on which row you're in. It almost says we've got independence between whether it's recent or not, and whether it's an early breakup, a medium breakup, or a late ice breakup. Our null hypothesis could very well be expressed in terms of independence. So let's go ahead and do that. Yeah, literally, I could say also the rate of a combination. Okay, and let's go with I'm going to go at IJ. Let's go with that. The chance of you being in row IJ, if I randomly choose one of these 93 years, it's equal to the rate of being in row I, and I'll call that pi I dot, okay, times pi dot J. Rate in row I. This is the rate in row J, rate in row J. And that would suggest something about the counts we would likely see. I'm going to say, let's just simply take how often, if the null hypothesis is true, let's take how often you should be appearing in any given row. And let's see, figure out how often that should be. I would expect the expected number in Yij in that location, the count in Yij is equal to the number of individuals in total in the table times the rate of occurrence in the row I, and that's just the sum in, I guess, the row I total over n times then the rate in J. Okay, so column J over n. And it turns out that our n's, a couple of them cancel out, and we end up with the row total times then the column total over the table total. Okay, so if I give you an expected count, that's what we should be seeing if, in fact, the null hypothesis is true. Okay, that's how you get the expected counts. You could do it by hand, but the software will give it to you for free. Let me just show you over here. Remember how we turn some things on and off in our contingency table? One of the numbers is the expected count. That's if, in fact, there is no relationship. Yeah, we did see 13 occurrences that were not recently, yeah, of the 63 years before 1980. 13 we did see as early ice breakup years before 1980. And then in the 30 years since 1980, we've seen 15 occurrences that were early ice breakup before 120 days. But the null hypothesis says I should have seen about 19 of them, literally 18.97 and 9.03 here. So these are the expected counts if the null hypothesis truly is correct. So we've got these numbers lying around, like how often should you see each of these occurrences, okay, if the null really is correct. And all we need to do is to calculate our number chi-square, and that looks like an x, but, you know, I'm trying to make it look like a capital Greek chi. That's equal to summing over across all the categories the observed count minus our expected count that we just calculated over here. Okay, take that difference and square it and divide through by the expected count. Literally, if we sum that across all 1, 2, 3, 4, 5, 6 cells, we should have exactly our chi-square value, our Pearson chi-square value, in this case, 9.043. So we've got a chi-square value. We would then get a p-value from our chi-square table, or JMP's probability distribution calculator. I'm looking at the time and I'm noting I've enough time to do just exactly that. So remember, our chi-square value is 9.043. Let's go ahead and show you how to get JMP's probability distribution calculator to give you then that result. Our distribution calculator. Yeah, go ahead, download that. And then open it. Boom. Come on, open it up. Okay, so we've got, yes, please open that. Notice that we have a couple things here. One of them is, well, it says normal. Let's switch that over to chi-square. It says we need this thing called degrees of freedom. And for this course, not for the follow-up course, but for this course, the non-centrality parameter is 0. Degrees of freedom. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So 1 is 2 minus 1 times, well, the number of columns is 3 minus 1. That's just 2. 1 times 2, 2 degrees of freedom. 2 degrees of freedom. Your chi-square value here is 9.043. Let's find an upper tail area above 9.043. We have a lower tail area being 0.9891. Our upper tail area, it's hard to barely see it, but it's 0.0109, exactly what our software answer gives us. Okay, so we're at a good place to stop. The lab today, which is due Monday, really highlights all the details of this chi-square procedure, and you should feel happy as a clam by the time the lab is over. But if you don't, you know what? You can send me an email or show up in office hours on Monday or just ask in class on Monday. That's a great place to stop. So what I'm going to do is stop the share, turn off the recording, and we'll see y'all soon.